Hey robotics teams. Today I thought I'd do a video on swerve drive. So both the Fargo and the Moorhead teams have purchased swerve drive modules, and so I've been doing some reading trying to understand, how it works and how it controls it. And I thought I'd do a video trying to explain how these things work. So in previous years we've done a tank drive where you've had uh, a set of motors on the left side and the right side of the robot, and if you drive them in the same direction, then the robot drives forward. If you reverse them, it drives reverse. And if you invert them, so one drives forward and one drives in reverse, the robot will rotate about its center axis. Well, with swerve drive, instead of having just one motor or one set of motors for the left and the right side, you have 8 total motors. You have 4 motors that drive each wheel independently, and you have 4 more motors that allow you to change the direction of the wheel um, in a 360-degree direction. And so the picture here is showing an example of a swerve drive system where you've got this drive wheel. This drive wheel can turn forward and backwards, and that would propel the robot around the field. And then you've got a second motor that you can use to rotate this wheel assembly 360 degrees, thereby allowing the robot to go left and right, things like that. Um, there's a cool example here. I'll play this video for a little bit. So this is an example that Hyundai did, basically a swerve drive car, where this car can do zero turn, it can crab left and right, it can do all kinds of crazy things, and that's what a swerve drive robot lets us do. We can drive diagonally, we can quickly rotate around our center axis, we can do all kinds of crazy stuff like that. So how does it work? Well, uh, gets into a little bit of math here, but if we've got some robot that is a certain width and a certain height, um, those drive wheels will be at each location at the 4 corners of the robot, and you can map this out. So if you get into high school where you take physics, this is called a static problem, where you can figure out like the force vector of a wheel driving. So this is all kind of basic physics stuff that you'll learn in physics. Then you get into things that are a little bit more complicated. So this gets into something called linear algebra, which if you go into engineering, you'll have to take some of this to understand. A lot of like machine learning is all linear algebra. Computer graphics, video games is all linear algebra. Um, but if we have velocities, so we have a Vx, a Vy, and an omega. So if we come back here, so Vx is our velocity forward and back, or at least think of it as away from you or towards you. And then Vy is the velocity left or right, kind of perpendicular to your viewpoint. And omega is the rotation about the center axis, where positive omegas, typically they're expressed in radians per second, would be counterclockwise, and negative omega would be negative radians per second, which would be clockwise. So if we've got these three velocities, Vx, Vy, and omega z, we can use the position offset of the motor drives and figure out what the velocity in the x and the y direction for each of these independent wheels, the 4 different wheels. And then from there you can look at the steering angle, which is just inverse tangent of the x and y velocity, and then the wheel velocity is just this quadratic equation here. Um, so now I wanted to show you a little bit about um, the WPI lib that we use. So in the past we've used this differential drive kinematics to try to understand where we are on the field. And with swerve drive it gets to be even more important because you can do something called field-oriented control. And that's where in the past, as you're driving the robot, you have to drive the robot with your perspective, thinking you're sitting behind the robot. And so if you push forward, the robot will go away from you. If you pull back, the robot comes towards you. If you push to the right, the robot rotates to your right. Um, and and that's called vehicle-centric control. But when you do swerve drive, it's better to do something called field-oriented control, and that's where when you're sitting in the Alliance station, if you push away from you, the robot drives away from you, and it doesn't matter what direction that robot is rotated, it'll always drive away from you. And likewise, if you pull it towards you, it'll come towards you. Left, it'll go left. Right, it'll go right. If you rotate counterclockwise or clockwise, the robot rotates. And so it doesn't matter what orientation the robot is, it's just if you want it to go across the field, you push away from you. If you want the robot to come back towards you and to the right, then you put the joystick down and to the right. Um, and so the WPI lib has already got a bunch of code to do all of this kinematics to figure out, if you want the robot to be going 1 meter per second to the right and 2 meters per second towards you while rotating at 1 radians per second, you can punch all of that into a function or a class, and it will produce the states for each of the 4 swerve units, and that state is the speed that motor should run in order to produce desired chassis velocity, and then what angle that motor should spin. Um, and so I ended up doing an example here in C++ that I'll show you in a bit. But this walks you through step by step exactly how you use it, how you can call these functions to get various information. So it kind of takes you step by step. And so that's the kinematics. The next thing is the odometry. And this becomes critically important in the autonomous mode, where the robot is trying to autonomously, automatically move from point A to point B. Okay, so that's me doing a lot of talking. So here's kind of a cool demo that I put together. So this shows swerve drive simulation. So let me just get the first Xbox controller here. So right now, you can see that, and we talked about this, that I'm trying to move the Xbox controller so that these values are roughly 50%. So you can see that, the state, this is the front left, front right, back left, back right motor. So right now they're just kind of in a random state. But if I push the Xbox controller away from me, we can see that the robot is going to move away from our position. So once again, if we're at the Alliance station and we push up or away from us on the Xbox controller, the robot's going to drive away from us. Likewise, if we pull back, it's going to drive back towards us. If I go to the right, it drives to the right. If I go to the left, it drives to the left. And of course, you can just, you can easily move this around into whatever direction. Okay, now the robot's standing still. Let's say we want to rotate counterclockwise, right? So I can use the Xbox controller. I can push the second joystick to the right, representing I want to rotate clockwise. And so here we can see that, one motor is going to be driving this direction, and this motor is going to be driving this direction, this motor this direction, this motor this direction. And you can see that that's going to generate this clockwise rotation about the center axis of the robot. Likewise, if I go the opposite direction, if I want to go counterclockwise, we can see those motors reverse, and the robot now will rotate counterclockwise. And now, let's say I want to rotate clockwise and drive away from me. So here the robot's spinning, clockwise away from me, and then suddenly I go like that. Now the robot is going to be rotating clockwise and attempting to drive away from me, or at least that's what I think it's going to do. I don't know. This is a simulation I put together for me to better understand how this swerve drive stuff's going to work. Um, so anyways, I hope this was informative and you learned something. Talk to you later.